So when we're dealing with trig functions, they have derivatives too. We still use power rule. Power rule is still a thing. Product rule is still a thing. Quotient rule is still a thing. Those still apply. But now we're applying them to trig functions. Okay? So the first thing I want you to look at is this graph here. This graph is the sine wave, right? The sine wave. Sine wave starts at 0. Or actually, it doesn't start at 0. It doesn't really start anywhere because it just repeats over and over and over. But let's say we start at 0. It increases until it gets to pi over 2. Then decreases, gets 0, 0 here at pi. And then it starts increasing again at 3 pi over 2. And then it does the same thing over and over and over again. Same thing. So if I were to continue this after 2 pi, it would keep going and do the same exact thing. Same exact thing. It just repeats itself. Okay, so this is sine. What we're going to do is figure out what the derivative of this is. I know the answer because it's at the bottom of the page, but I want to see, picture we didn't know that. So let's look at this guy. So derivatives, we just talked about it a few minutes ago. Derivatives are slope of the tangent line at a certain point, right? That's what derivatives are. So let's find derivatives of this guy. Let's start here. Actually, let me use a different color here. At pi over 2. So the sine of pi over 2 is positive 1. Okay, that's what it says. That's what it says on your tables that I gave you, and that's what it says on here. Here's the question I'm going to ask. What is the derivative of sine at pi over 2? What is the derivative of sine at that red dot? 0. Yeah, why is it 0? No. So let's go back to what is a derivative. A derivative is a slope, right, of the tangent line. So what does tangent mean? It means it hits at one spot. So if I were to draw a line here and only hit the red dot and the graph, so the dotted graph and the red dot at one spot, what would that line look like? It would have to look like this. It would have to look like that. It's the only way it could look. Because if I were to do it a different way, it would hit at multiple spots. So that blue line is tangent to sine graph at the red dot. That's what a derivative is. Okay? So my next question is, what is the slope of that blue line? 0. Yeah, it's 0. Constant, right? Doesn't go up, doesn't go down. It's just, there's no rise, it's all run. Doesn't go up, doesn't go down. It just kind of goes. It kind of goes side to side. So we're going to go write that in our table. In our table, f prime means the slope. The slope of the tangent line at pi over 2 is 0. Is there anywhere else on the sine wave where I would have a 0 derivative? 3 pi over 2. Yeah, look at 3 pi over 2. It's the same idea, right? Instead of being the top, instead of being a maximum, this one's a minimum. It would have the same issue right here, right? So at 3 pi over 2, let's put 0. Okay. So we got a couple of those. We're not going to fill all of these out. I just want to fill enough out so I can get a picture of what this is looking like. So far I have 2 dots. The derivative at pi over 2 is 0. The derivative at 3 pi over 2 is 0. Okay. me erase these. Let's look at this dot right here. The starting dot, 0. How would the slope of the tangent line look at 0? Would it look horizontal like the last one? No, it wouldn't, right? This one has more of a slope, right? Kind of look like that, right? What is the slope at 0? At that red dot, what is the slope of that blue line? It looks like it's 1, right? How do I know that? Because we go over here, and how much am I going over here? Up 1, over 1, right? Up 1 unit, over 1 unit. This is 1 unit right here. This is 1 unit right here. So it looks like I'm going up 1, over 1. 1 divided by 1 is 1. So the slope at 0 looks to be close to 1. If not exactly 1, it's pretty close to 1. Is there anywhere else where I would have the same slope? At 2 pi, right? At 2 pi, it's the same situation, right? I would have a slope that's parallel to that one. So that one's going to be 1 as well. What would the slope of the tangent line be right in between those at 1 pi? So at this dot right here. So a 1 would look like this, right? Is that the slope of the, is that the correct tangent line at that dot? No, it's close though. It would be the opposite, right? Yeah, it would be the opposite. I would need to flip this guy around. It would be going in the opposite direction. It would look like that, right? That is -1, right? From 3, go down 1, over 1, around 1. Might not be exact, but it's around 1. Okay.
Is it -1?
Oh, sorry, -1. Yeah, sorry. You guys just said that. Sorry. Okay. I'm not going to fill in the rest, but I want to kind of get an idea. Okay, so let's look at a red dot in between. So we know what the slope is at pi over 2 and 3 pi over 2, right? We said 0. What about in between the red dots? So what about in between these red dots here? So let's say pi over 4. So that tangent line would look like that. So the one at 0 was 1. The one at pi over 2 was 0. What about the one I just drew? It'd be something in the middle, right? It'd be something in the middle, between there, right? So are the slopes, to get from this red dot to this red dot, are the slopes increasing or decreasing? Decreasing, right? From 1 to half to 0. So they're decreasing. And then they go down, and then they do the same thing. Okay? So let's kind of get a picture of what's going on here. Let's kind of get a picture. Let me erase this and draw what we got. So now I'm going to draw the points we have here. Use a different color. Okay, so I'm going to draw the down here. I'm going to draw these dots, these 5 dots here. 0, 1. Pi over 2, 0. pi, -1. 3 pi over 2, 0. 2 pi, +1. If I were to connect those orange dots, what would it look like? Yeah, wouldn't it look like that guy down there? That orange guy looks exactly like the guy below it, g of x down here, right? So that's why the derivative of sine is cosine. Because when you graph all the derivatives, guess what you get? Cosine. So the derivative of sine is cosine, which it says at the bottom, right? That's why that one happens. Okay? Let's look at the next one now. Let's look at g of x now. So let's do the same thing. Where on this dotted line would I have a slope of 0? 2 pi? Where else? 0? Anywhere else? Pi, yeah. Anywhere there's a maximum or minimum, right? A top or a bottom. We call those, that's where you would have 0 as a slope, because the tangent line would look like that at all of those spots. The tangent line would be a horizontal line. So let's fill in the table. So at 0, the slope is 0. At pi, the slope is 0. At 2 pi, the slope is 0. So any positive ones or negative ones? Pi over 2, -1, good. Pi over 2 is going to have a -1 slope. So pi over 2, -1 slope. Where else? It's going to have a +1 slope. Good. Got 5 dots. We got enough for 5 dots, right? So let's go. Let me go make those 5 dots, just like I did the last one, and see what kind of picture it shows us. See if it shows us anything different. So at 0, 0. Pi over 2, -1. Pi 0. 3 pi over 2, +1. 2 pi 0. Orange guy now. Does that guy look familiar at all? Kinda, right? Where does it look like? Keep going. It's sine. Looks similar to sine, except, yeah, doesn't sine usually start up and then go down? So it's looking like it's doing the opposite of what sine is doing, right? In math, how do we say opposite? How do we know something is opposite? Put a negative, right? Put a negative in front. So it's opposite of sine. If sine goes up, this guy's going down. If sine goes down, this one's going up. It's just the opposite, right? So that's why these two guys are true. So we just proved mathematically why these guys are true. That's what we just proved. We just proved those two true. Why is derivative of sine cosine? Well, that's the first picture. Why is the derivative of cosine negative sine? That's the second picture. Okay? I can prove all of these guys, all 6 of these guys, but I'm only going to prove one more. I proved 2 visually with graphs, right? So I'm going to do tangent. So on the next page, we're going to prove why tangent, the sine of tangent, or sorry, why the derivative of tangent is secant squared. Okay? All right, so let's turn it over to the back. We'll do one more proof, quasi-proof, and then we'll start doing some problems. Okay, so we've proven why sine, derivative of sine is cosine. We've proven why derivative of cosine is negative sine, right? So now we're going to prove why is the derivative of tangent secant squared. Okay. All right, so what do we know about tangent? Tangent of x. This is where it gets a little confusing because when you hear tangent, you're like, is it tangent line or is it, when I talk about tangent, I'm talking about tangent. Tangent, y over x, opposite over adjacent. That's what I'm talking about here. So we know that tangent, I just said it, we know that tangent is y divided by x, which is the same thing as opposite over adjacent when we're finding it on a triangle, right? What else do we know about tangent? Kind of related to those 2 guys. What's another way of finding tangent besides y divided by x or opposite divided by adjacent? Yeah, isn't sine y over 1? So in other words, y is sine, and x over 1 is cosine. So isn't tangent really just sine divided by cosine? Okay. Well, let's go do that. So let's rewrite tangent. Tangent of x equals sine of x over cosine of x. So what I'm going to do now is I'm going to find its derivative. Except I'm going to use that guy there. Because sine divided by cosine is tangent. So they're the same thing. How would I find derivative of the guy in yellow? Which one of my rules would I have to use? Power rule, product rule, quotient rule. I have to use quotient rule, okay? All right, so quotient rule says, let's write this out. Low. So what is the low? Cosine. So I'm going to rewrite cosine. Cosine of x times the derivative of the high. What is the derivative of sine? Cosine. We just learned that, right? Minus the high. What's the high? Sine times the derivative of the bottom. So high d low. Derivative of the low. What's the derivative of cosine? Negative sine. Over bottom squared or low squared. Low times low. So in other words, that would be, so in trig, they put the squared there. I don't like that. I prefer the squared here, but that's where they put it in. It doesn't matter. So in trig, it doesn't matter. Just sometimes in trig, they put the squared. You see where it's secant squared is right there? They put it there. I don't really like that, but that's what they do. So sometimes it's there. Okay, so let's combine this. Let's simplify this a little bit. What's cosine times cosine? Cosine squared. again, I put the squared here. They put the squared between the cosine and x. It doesn't matter. So I have a negative. So if I distribute that negative, it becomes positive and positive. So plus sine of x squared over cosine of x squared. Okay. There's only one identity that you're going to have to, that sometimes it'll come up. One trig identity, and it's the most popular one. There's a trig identity that says it actually says sine squared equals 1, right? Why is that true? What is that? Why is that identity true? What are we talking about here when we're talking about this? The unit circle. This comes from the unit circle. What is the unit circle made up of? A bunch of the unit circle when we want to find all these values, we use a bunch of triangles, right? Triangles, right? What type of triangles? Right triangles. And didn't we say that sine is y? So isn't this really just y squared? Cosine is x squared. Hypotenuse is always going to be 1. What does that look like when you're talking about right triangles? You learned it probably in 7th grade, 8th grade maybe. Right triangles. No, has nothing to do with degrees. It's one of the most popular things you guys remember. Starts with a P. Pythagorean theorem. Pythagorean theorem. Here's your a squared. Here's your b squared. And what's c squared? C squared is always going to be 1. That's why this guy doesn't get a squared. Why doesn't this guy get a squared? Well, what's the squared for 1? Always 1, right? So it's called the Pythagorean identity. Okay? So anytime we see that, we always change it to 1. This guy here is equal to this guy here. Just comes from the Pythagorean theorem. Right triangles. That's why that's 1. Cosine squared. Cosine squared stays cosine squared. Well, what is 1 over cosine? What is the reciprocal of cosine? Not cosecant. It's actually secant. It's actually secant. So that's why the derivative of tangent is secant squared. That's a little proof. It's not really a proof, but it's why the derivative of tangent is secant squared. I could do that with all of them. I'm not going to because we have other stuff to get to, but it's why the derivative of tangent is secant squared. Why is the derivative of cosine negative sine? Why is the derivative of sine cosine? All of this stuff. Okay, so like I said, I could do the same thing for the next two, for the last three down here, but we just don't have time. Okay, but that's why they all are what they are. So why is the derivative of cotangent negative cosecant squared? Why does the derivative of secant have itself times tangent? Because if I had time to prove it, I would show you. Okay. Okay, so now let's start getting to problems that you're gonna see. These are the problems you're gonna see. Find the derivative of f of x. F of x. X squared, sine squared. What are x squared and sine squared doing to each other? Mathematically, what's happening there? Mathematically, what's happening to sine squared and x squared? They're being multiplied together, right? They're being multiplied together. Multiplication. They're two functions on their own. They're separate functions. X squared is its own thing. That would be a parabola. Sine of x is its own thing, right? So they're two functions being multiplied times each other. That's when we use product rule. That's when we use the product rule. Okay? Product rule says the derivative of the first times the derivative of the second. Well, the derivative of sine is cosine plus the reverse. The derivative of the first, 2x, times the second. Those guys aren't like terms. There's nothing like about them. So we're done. Okay. All right. So here, let's do b now. Cosine of x divided by x. First thing, I see this even in calculus. Can I do that? No, because the top is not an x, it's an angle. It's an angle, cosine of something. Now, if I had an x out here, like that, then go for it. Absolutely. But I can't do, that doesn't work. Okay, that does not work. Okay, so I have cosine of x divided by sine, but divided by just x by itself. Again, those two guys are separate functions. This guy does its own thing. This guy does its own thing. They each do their own thing. So if I'm dividing them, if it's a division problem, to find the derivative, I have to use the quotient rule. I have no other option but to use the quotient rule. Okay, so like we just did, low times the derivative of the high, negative sine of x, minus the high times the derivative of the low, which is just positive, over the low squared. Okay, so I got to distribute the negative here. So I get negative x times sine of x minus cosine of x over x squared. Again, the top, there's no like terms. One is sine of x, one is cosine of x. Oh, because I had a, so I had, this is a -1, right? This is a -1. So I just moved that -1 to the front because it's multiplication. So I can do that just so that the negative's in the front. Okay. Actually, you could go a little further. You could do this. You could give them both x squareds. You could do that. And if you did that, you cancel out one of these guys with one of those guys. So you'd get negative sine of x over x minus cosine of x, x squared. Again, most of the time you see these, you'll see them on multiple choice questions. Both of those guys I boxed are the same answer. But sometimes you'll get here, A, B, C, D don't look like that. And you're like, uh-oh. One of them might look like that. Okay. Has nothing to do with calculus, just factoring, right? Factor out an x. But I always try to give you both answers just in case. If it were a free response, either of those answers would be fine with me. If you got the top, great. If you got the bottom, great. But most of the time, I'm telling you right now, most of the time you see these problems, this chapter is full of a lot of multiple choice type questions. There's not a lot of stuff we do in this chapter where you're going to see on a free response. Now, you'll have a free response section, but I have to kind of create them. Most of this is free response or multiple choice questions. Okay. Okay. Now let's look at C. Okay. So now square root of t and secant of t are being added together. Not multiplied no more. They're being added together. Okay. So the first thing I'm going to do is rewrite g of t, sorry. Instead of t, square root of t, I'm going to give it a power. I'll put parentheses around t just because it's not x anymore. So just to kind of, that's the angle. So now we're not going to use the product rule. We're not going to use the quotient rule. We don't need to. We're not multiplying or dividing. I'm adding. So what I'm going to do is I'm just going to find the derivative of each. T to the 1/2. Move the 1/2 to the front. Subtract 1 power from the power. Plus the derivative of secant is secant of x times tangent of x. Yeah, it's secant of x times tangent of x. So in our case, we're not using x. We're using t. So everywhere there's an x, we got to put a t instead. Okay. So secant of t times tangent of t. Again, that answer probably won't be on multiple choice because it's got negative exponents. So negative exponents, so let's rewrite this. 1/2. Since it's got a negative exponent, t is going to have to move to the bottom, and it's going to be a root because it's 1/2. Okay. All right, let's try letter D. 2 more and we're done. H of S. So I have two things, two functions going on here. I have 1 over S, and I have 10 times cosecant of S. They're being subtracted, so I don't have to use the product rule or the quotient rule. But look at 1 over S. That's a fraction. How do I find derivative of the yellow stuff? How do I find the derivative of the yellow stuff? That's my first question. That's what I got to do first. So how do I find derivative of the yellow? I could use the quotient rule. I could use the quotient rule. It's such a simple fraction, though, that is there a way I can go around the quotient rule? Is there a way I can rewrite it so I don't have to use the quotient rule? So how would I rewrite it? S to the what power? -1, yeah. I would rather use that way. Could you use quotient rule? Absolutely. But that's just a lot of extra work for really no reason. That way, you just use the power rule. H prime. Multiplied, bring the -1 to the front, times S to the -2 power. 10's just coming along for the ride. 10's a coefficient, so don't worry about 10. Just find the derivative. So the derivative of cosecant is negative itself times cotangent. So negative itself times cotangent. So negative itself times cotangent. It's a lot of negatives there, so I'm going to put some parentheses just to, I'm multiplying those two. Those are multiplication. Oops, no, I put it in the wrong spot. I'm supposed to be subtracting those two, sorry. Everything inside the parentheses is being multiplied. In between them is subtraction. So let me clean this up a little bit. So -1 s squared. That's what that would be. Minus -10 cosecant of s times cotangent of s. Well, a negative times a negative makes a positive. Because really this is a -1 here. It's got a negative in front, there's a -1 there. So really what I did was I multiplied 10 times a -1 to make -10. And then there was already a negative here, so they cancel that. Okay. Okay, last one. I want you to do the last one. Try the last one on your own. Then we'll be done. So you're multiplying x times cotangent of x. So first times the derivative of the second. The derivative of cotangent is -1 negative cosecant of x squared of x. Then the derivative of the first times the second. And you're done. I'm not going to give you another problem, but I'm going to give you another example. You don't have to do this problem, but you'll see this problem too. So 5 times the cotangent of x. Do I need to use the product rule for this guy? Do I need to do the exact same thing I just did with the last guy for this guy here? Because it's 5 times this guy. This is a big mistake I see. 5 is a coefficient. It's just going along for the ride. So you don't need to do the whole product rule for that. X is a function. So that's why we have to do the product rule. So a lot of times I see students doing product rule for this guy and this guy. You don't need product rule for this guy. Just use the regular power rule. So it's going to be 5 times whatever it is, -1 cosecant squared of x. So it would be -5 cosecant squared of x. You don't have to use the product rule for that guy. Okay. All right. Okay, so tomorrow I'll give you some practice on that. And then the rest of the week, we're going to be doing chain rules. So starting Wednesday, Thursday, and Friday, we're going to be doing chain rule stuff. Chain rule is the last big rule that we use for derivatives. That's the last big rule, the chain rule. And it takes a couple days because there's a lot of parts to it. So most of it we'll do on Wednesday and Thursday, but we might not finish till Friday. So some of you I know won't be here on Friday because of the rally and everything.